Hello and welcome to this demonstration of the atomic magnon detector, a detector of only 11 atoms that can detect magnetic waves. First, let us take a look at what a magnetic wave is. For that, let us consider magnetic atoms in a row. These atoms have a magnetic moment, a spin, which can point in any direction. One way to understand this is by imagining the electrons in the atom spinning around very fast, causing a magnetic field, much like how an electromagnet works. We put these atoms, or spins, in such an environment that the magnetic north pole prefers to point up. That is indicated by these arrows. This is their ground state, the state which has the least amount of energy and is therefore the most favorable. A magnon, or magnetic wave, is then an excitation of the state that gets delocalized along the chain, meaning it spreads out along the chain. A chain can have multiple of these magnons, as shown. So far, we have considered all atoms to point up. We can say that neighboring atoms are ferromagnetically coupled. It's also possible, depending on the environment, for the atoms to point in opposite directions. This is called antiferromagnetic coupling. Even in this picture, a magnon can be interpreted in the same way. Now the goal of this research is to figure out whether a magnon, which started here on the left, will reach the end of the chain. This is usually very difficult because these magnons die within a nanosecond. To overcome this difficulty, we place an 11 atom large sensor at the backside of this chain. If the sensor feels the magnon, it will trigger a switch, which we can later see by checking the state of the sensor. So, how does this sensor work? Let us take a look at a sensor with an input chain of 3 atoms. We can see 3 subchains, one of size 3, one of size 8, and another of size 3. Colloquially, we call this a 383. Now let us look closer at a set of 3, also called a trimer. The first thing to notice is that spins point either up or down. This is due to how the atoms lie in the crystal structure underneath. You may also notice that neighboring spins are pointing in opposite directions. As mentioned before, this is due to an anti-ferromagnetic coupling. This coupling is a result of how the atoms bind to the surface and their relative positions. Furthermore, the majority of the spins, 2 in this case, are pointing up. This is because we have an external magnetic field of up to 1.5 Tesla, which forces the majority up. These 3 ingredients are the basis of our sensor. Now let us go back to our 383. Based on the rules we just established, we can see that the 8 in the middle will have 2 degenerate ground states, 2 states that the 8 prefers to have, called A and B. Now between each chain there is a weaker ferromagnetic coupling. This favors like direction. So on the left it would be happy, while on the right it is unhappy. And even when the 8 switches, we will always have one side happy and one side unhappy. Using a very, very sharp needle, the same one that we used to build the structure, we can make an excitation in the inputs. This causes the trimer to flip. Now the 8 is unhappy on both sides, and so it prefers to switch. This is a sign that we detected an excitation. For example, a magnetic wave reaching the end of the chain. Now we can go to the other side and repeat the process to bring the 8 back to state A. It's important to notice that this is a one-way button. Another excitation on the right will not switch the 8 again. After all, it is already happy on both sides. And just like that, this sensor of only 11 atoms can detect an incoming magnetic wave. Thank you for your attention.